Hi, this is Mr. Mack. Now, this video is going to be proofs of the product rule, the quotient rule, and I think I'm going to throw in also on this one the proof of the chain rule. So first of all, product rule. What we want to do is we want to prove that the derivative with respect to x of f of x times g of x is equal to f of x times g prime of x plus g of x times f prime of x. Okay, so to start with, we're going to say the derivative with respect to x of f of x times g of x is equal to the limit as h approaches 0 of f of x plus h times g of x plus h minus f of x times g of x all over h. Now, you can probably notice here that I left a big space in the numerator of our fraction, and that's because I'm planning on adding 0. Now, how am I going to add 0? What I'm going to do is I'm going to add, actually, I'm going to subtract g of x plus h. No, let's do this. I'm going to subtract, what am I going to subtract? I'm going to subtract f of x plus h, g of x plus h, no, g of x, g of x, plus f of x plus h, g of x. Yeah, that'll do it. Now, in the numerator, I could group these two terms together, and I can group these two terms together. If I do that, I can do a little algebra, and I get this is equal to the limit as h approaches 0 of, pull an f of x plus h out of the numerator, f of x plus h times the quantity g of x plus h minus g of x. And now this fraction is going to have h as a denominator, so I'm going to put the h right here. And then that's equal, plus the limit as h approaches 0 of, now I'm going to pull out of this one a g of x, and that's times the fraction f of x plus h minus f of x over h. I'm going to put the h underneath there. And now let's take some derivatives. As h approaches 0, f of x plus h becomes f of x. Now, as h approaches 0, g of x plus h minus g of x all over h is g prime of x, because that's the definition of the derivative of the function g. Now, plus the limit as h approaches 0 of g of x is just g of x, and the limit as h approaches 0 of f of x plus h minus f of x all over h is defined to be f prime of x. And that's what we wanted to get to, so we're done. We can just say QED. Now, a student has arrived for some help, so I'm going to pause this video and I will come back to it. So see you in a couple minutes. Hi, I'm back. Now, let's go to proving the quotient rule. Now, prove we want to show that the derivative with respect to x of f of x over g of x is equal to g of x times f prime of x minus f of x times g prime of x over g of x quantity squared. Now there is a mnemonic for this. If g of x is the low function and f of x is the high function, you can remember this as low d high minus high d low over low low. All right, so to start with, let's agree that the derivative with respect to x of f of x over g of x is equal to the limit as h approaches 0 of f of x plus h over g of x plus h minus f of x over g of x all over h. That's the definition of the derivative. Now, algebra ensues. So this is equal to the limit as h approaches 0 of f of x plus h times g of x minus g of x plus h times f of x all over h times g of x plus h times g of x. Now, guys, I hope you don't have trouble with this h in the denominator. See, we're dividing everything by h. So that would actually be the same thing as multiplying here by 1 over h, which would put the h in the denominator, which is where I have it. So I hope you're okay with that. If you need more on that, let me just suggest that you pause a moment and consider it yourself. I think you'll come to the conclusion that what I've done is right. Now, I'm going to add 0 in here. Notice I've left a spot to add 0 again. And the 0 I'm going to add is going to be minus f of x times g of x plus f of x times g of x. Just convince yourself that I've added nothing to the numerator of that, and that's all right. Now, I'm going to group these two terms, and I'm going to group these two terms. Now, out of these first two terms, now this is equal to the limit as h approaches 0. Now, out of the first two terms, I'm going to pull a g of x. So I have g of x, and that's going to be times f of x plus h minus f of x. Now, out of the second two terms, I'm going to pull a negative f of x. So minus f of x, and I'm left inside with g of x plus h minus g of x. Now notice I've turned those around. This one came down here, and this one was over there, because I took the negative sign, I took a negative sign out here, which made this term, which was negative, positive, and it made this term, which was positive, negative. And now this is all over g of x plus h times g of x times h. Now, some algebra ensues, and some of this may be a little confusing, but see, if you have a fraction and the numerator has terms, you can split the fraction up into the numerator terms, and each of those terms will be over the denominator. So what I'm going to do is I'm going to do that partially, and I hope that you can see that this is algebraically equivalent. If not, some other steps might need to be put in here too. Let's do this. This is g of x times f of x plus h minus f of x. And I'm going to take the h and put it up here, minus f of x times g of x plus h minus g of x. And again, we need an h there in that term. Now, still in the denominator is g of x plus h times g of x. Now, you need to convince yourself that what I've written is algebraically equivalent. This term here, I've put the h underneath the second part of it, and this term here, I have again put the h under the second part of it, and that is equivalent to where it was in the denominator of the whole thing. Now I've left the g of x plus h and the g of x in the denominator. Now we are ready to take some limits. First of all, the limit as h approaches 0 of g of x is g of x. There's no h in it. Now, the limit as h approaches 0 of f of x plus h minus f of x over h is f prime of x. Minus the limit as h approaches 0 of f of x is f of x. And the limit as h approaches 0 of g of x plus h minus g of x over h is g prime of x. Now, in the denominator, the limit as h approaches 0 of g of x plus h is g of x. And that's being multiplied by another g of x, so we have g of x squared. And we have the result we expected. We can say QED, or quite easily done. One more. Let's do the chain rule. Now, what we want to do this time is we want to prove that the derivative with respect to x of f of g of x is equal to f prime of g of x times g prime of x. Now, first of all, let me just say to you that both f and g have to be differentiable, and the range of g has to be in the domain of f. But assuming those things, and those are things that do need to be assumed, we can say that the derivative with this is what we want to prove, by the way. So our first step, the derivative with respect to x of f of g of x by the alternate form of the derivative is the limit as x approaches a of f of g of x minus f of g of a over x minus a. Now, what I'm going to do this time is I'm going to multiply by 1. Remember, in the last two, what we did was we added 0. Anytime you want, you may add 0, because 0 is the additive identity. Anytime you want, you may multiply by 1, because 1 is the multiplicative identity. Now, the one I'm going to multiply by is g of x minus g of a over g of x minus g of a. And now this then becomes the limit as x approaches a of f of g of x minus f of g of a over g of x minus g of a times g of x minus g of a over x minus a. One more thing. If g of x is a continuous differentiable function as x approaches a, it is true that g of x approaches g of a. So now we can rewrite this as the limit as g of x approaches g of a of f of g of x minus f of g of a over g of x minus g of a times the limit as x approaches a of g of x minus g of a over x minus a. And then finally, point out that the limit as g of x approaches g of a of f of g of x minus f of g of a over g of x minus g of a is f prime of g of x. And the limit as x approaches a of g of x minus g of a over x minus a is g prime of x. And once again, that was quite easily done. Okay, that's going to be all for this particular video. I'll look around and see if maybe another one needs to be produced, but these are 3 very important proofs, and I'm going to stop at this point.